So very good morning students. In today's class we are going to solve problems based on bilinear transformation. In the last video we have learned what is bilinear transformation and what is the purpose of bilinear transformation, like converting a analog IR filter to digital IR filter. So now we are going to apply that bilinear transformation and we are going to design a digital IR filter. So here we have a problem statement. Design a second order low pass Butterworth filter with a cutoff frequency of 3.4 kHz at a sampling frequency of 800 Hz. So this is the problem statement they have given. So how to solve this problem? So what are the data specifications they are given is the order is 2, that is n is equal to 2, and you need to design a low pass digital Butterworth filter and the cutoff frequency is given as 3.4 kHz and the sampling frequency is 8000 Hz. So first let us convert this specifications into the digital frequencies, that is omega d is equal to 2 pi f. So convert this 2 pi into frequency, which is 3400 kHz. Thereby we will be getting the omega d as digital frequency as 6800 pi radian per second. And then time t, that is the sampling period, capital T is equal to 1 by f, which is 1 by 8000. Now let us do step by step. So first we will be doing the pre-warping. So what is pre-warping is you need to convert the given analog specification, digital specifications into analog specification first. So for that we have the formula WA is equal to 2 by T tan omega T by 2. So let us substitute 2 by T as 2 divided by 1 by 8000, which is 16,000 multiplied with tan of omega d. Omega d is 6800 pi divided by 1 by 8000 whole divided by 2. So if you simplify, you will be getting omega a as 6.6645 into 10 power of 4 radian per second. So the second step is, as already they have mentioned, the order is 2. So directly we can write it from the table. What is the Butterworth filter polynomial? That is HP of S is equal to 1 divided by Bn of S, and Bn of S for order n is equal to S square plus 1.414 2s plus 1. So this is taken from the tabular column where you have the list of the values of n. For that each value of n, what is the Butterworth polynomial? So for n is equal to 2, this is the Butterworth polynomial. Directly we have written here, and even you people can keep in memory all this Butterworth filter polynomials for different values of n. So let us apply the transformation. That is, first we will be converting this low pass to the given low pass specifications. So for that the transformation formula is H of S is equal to HP of S divided by omega A. So wherever you have S in this particular transfer function, you just replace with S divided by omega A, whereas omega A is 6.64. See, just now we have calculated 6.6645 into 10 power of 4. Just let us substitute here in this complete transfer function, and the simplified form is this. So now we will apply the bilinear transformation. See, why we are going for this bilinear transformation is, so far we have designed only the analog IR filter. Now in order to convert it into a digital IR filter, you have to apply the transformation, and the transformation is nothing but S is equal to T into Z power minus 1 divided by S. So this is the transformation for the bilinear transformation. So let us apply here. So wherever S is there, I am going to replace with 16,000 into Z minus 1 divided by Z plus 1. So after substituting here in the given transfer function, that is HA of S, we are getting the transfer function as H of S. So once you convert that analog transfer function into digital transfer function, it is represented as H of Z. Then let us simplify this equation by taking the numerator and denominator, multiply with 16,000 square, so that you can simplify it. Again we will simplify by multiplying the numerator and denominator with Z plus 1 the whole square, and then again we will simplify once again, and the final value is H of Z is equal to 0.7157 plus 1.4314 Z inverse plus 0.7151 Z power of minus 2 divided by 1 plus 1.349 0 z inverse plus 0.514 z power of minus 2. So this is how we are able to generate the transfer function of your digital IAR filter using bilinear transformation. So this final transfer function expresses the transfer function of your digital IAR filter using bilinear transformation. So the next problem is, again you are going to design a digital low pass Butterworth filter for the given specification as 3 dB attenuation in the passband and 10 dB stop band attenuation, and the passband edge frequency is 1.5 kHz and the stop band edge frequency is 3 kHz and the sampling frequency is given as 8 Hz. As we are done in the previous problem, in the same way, first we will converting the given digital into analog frequencies. So the formula is 2 pi f will convert. So first we will convert the digital frequencies into omega, so that 2 pi 1500 you will be getting as 3000 radian per second. And similarly the other cutoff frequency 2 pi into 3000, which is 6000 pi radian per second. And we know the sampling period is 1 by s, whereas fs is given, that is the sampling period is given in the problem statement as 8000. So put it as t is equal to 1 by 8000 second. So as per the procedure, the first step we need to pre-warp it. So what is pre-warping? I have told you, it is converting the given digital specification into analog specification first, then we'll be designing the analog filter, then we'll convert that analog filter into digital filter. So for that case, the pre-warping equations are omega ap is equal to 2 by t tan omega t by 2. So let us substitute the t value and omega d and t. You are getting the WAP as 1.0691 into 10 power of 4 radian per second. And similarly omega AS is 2 by t tan omega t tan omega dt by 2. So substitute the values of t and omega d. We are getting omega AS 3.8627 into 10 power of 4 radian per second. Then parallelly we will calculate what is Vs. So Vs is nothing but WAS divided by WAP. So let us divide these two values and we are getting Vs is equal to 3.6130 radian per second and the stop band edge frequency is given as 10 dB. Next let us calculate the order of the filter. So for that you have to calculate eta square, which is 10 power of 0.1 into 3 minus 1, and the values seem to be 1 here. Then we'll calculate the order of the filter. So the order of the filter, already we have the formula log of 10 power of a into 10 minus 1 divided by 2 log of omega p by omega s. So by substituting this we are able to calculate what is the order of the filter, and we are getting the value as 0.8553, and this has to be approximated to the, that is it has to be round off to the next term largest integer value as 1. Hence we choose n is equal to 1. So for n is equal to 1, the Butterworth filter polynomial is s plus 1. So from the tabular column for n is equal to 1, we have taken the Butterworth polynomial, and this represents the transfer function of your analog filter. Now let us convert this transfer function analog filter into digital IAR filter. Before that, let us convert this low pass to low pass transformation so that the cutoff frequency will be met. So for that you have to replace s with s divided by omega ap. Then after replacing that, you are getting the transfer function which takes this form. Then finally we will apply the bilinear transformation. As you know, the bilinear transformation is 16,000 into z minus 1 divided by z plus 1. So whatever the transfer function you got it here, this represents your analog filter. Now we'll convert this analog filter transfer function into digital filter transfer function, which is h of z, by applying the transformation s is equal to 16,000 into z minus 1 divided by z plus 1. So after applying the transformation, okay, we are getting h of z which takes this form. So in order to simplify this, let us multiply with 16,000. Again, once again, in order to remove z plus 1, I am just multiplying with z plus 1 and divide by 1. We are getting h of z which takes this form. Again, we are dividing it so that we will be getting the transfer function in terms of negative powers of z. Always remember, the transfer function of any filter, it has to be represented both the numerator and the denominator polynomial in terms of negative powers of z. So this in order to make it, I am just multiplying with 1.6682 into z and then dividing with that, so that the final transfer function takes the form of h of z is equal to 0.4006 plus 0.4006 z inverse divided by 1 minus 0.1989 z inverse. So this represents the final transfer function of your digital IAR filter, and it is built using the bilinear transformation. Okay, so based on the same procedure, you can solve any problems, whether it is a high pass, band pass or band stop filter also. Okay, thank you. Thanks for your time. Let us continue in the next video. Thank you.